Welcome into another session of virtual classes of science here, in which we are into the theoretical aspects of capacitors, which is a very important session in electrostatics, that is the first unit of second year physics. Here I am going to do one problem, I can say one simple problem, which is very relevant and important when it is concerned with your board exam as well as entrance exams. So that problem we will call it as capacitors, which is sharing charges. So problem is between two capacitors when they share electric charges. So I hope all of you have got the previous concepts that we have done in electrostatics and you know basics of capacitors. That is what I take it as a granted value or granted knowledge from your side. Or at least I expect that all of you know that that is, we all know what is capacitance, that is capacitance is equal to charge divided by potential. Now we are going to see this one as before sharing and after sharing. So first situation I am taking it as before. We have one capacitor, say it has got a capacitive C1 charged to a potential of V1 and whose plates are having plus Q1 and minus Q1 respectively. So I can write the charge content of the capacitance is Q1 is equal to C1 V1, simply the product of capacity and potential. And the potential energy, we know that potential energy can be written in different forms. I am writing that one in form of C and V. So the first one has got a potential of say half C1 V1 square. And similarly, if I have got another capacitance or a capacitor, say C2 charged to potential V2 plus Q2 minus Q2 are the charges on each plates. I can write for this is for the first and for the second one. I can write the charge content is equal to C2V2 and the potential energy as half C2V2 square. This is the condition before sharing or before I connect the charge capacitors. So put together I can say before connecting or before sharing starts, the total charge content of capacitance 1 and 2, I can write it as Q before is equal to C1 V1 plus C2 V2 and the total potential energy before is half C1 V1 square plus half C2 V2 square. This is very simple. You know everything what is happening before that. Now we are into a connection. I mean after connection what is going to happen. So we are going to connect the capacitances, say C1 plus minus C1 with C2 plus minus in such a way that the positive is connected to positive and the negative is connected to negative. Like to like connection is known as a parallel connection. So we are connecting this one parallelly. When it is connected parallelly, what is the possibility? What can happen in the system? We know that we have connected capacitance 1 charged to potential V1 with V2. Let us assume that V1 is greater than V2. That means there is a potential difference. Higher potential and lower potential. Higher to lower, there can be a flow. Higher to lower, there can be a flow. What is flowing here? What is free to flow? The free to flow material is nothing but the charge will flow. We can say that there will be a flow of charges through which one? Through the wires, okay? Through the connecting wires. When the charge flows through the wires, it is called as a current flow, we can say, and that will lead to what? A protection of heat energy. Obviously, there can be loss of energy. So what is the process? We have seen that the two capacitors charged to different potentials are connected by means of wires, and since there is a potential difference, there is a flow of electric charges from the higher potential to the lower potential, and that can lead to what? Loss of energy. That means a final potential energy will be less than the initial potential energy. That is what we are expecting. We will see what is that, whether it is true or false. So, till when, until which moment it will flow? This will flow till what? Suppose there are two columns in which I am filling water. This is filled fully and this is filled half. If I connect them with a tube, what will happen? Water will flow from the higher column to the lower column. Till which level? Till they attain a common value, common height. Or we can say that the flow will happen till they attain a common potential. So that is what we are going to see for the first. So we are going to start the analysis. Okay? Yes. So we are going to start the analysis of the problem. So after connection, say we know that this is a parallel connection. Parallel connection of two capacitances. Effective value of capacitance, that is C after, is nothing but the sum of the two capacitances. We know that it is C1 plus C2. That will be the value of the final capacity of the system. Now if that is connected like that, what will be the final charge value? Final charge value, charge content after. We know that charge is a conserved quantity. Nothing will happen for the charge even if it is connected or disconnected. So that will be simply equal to what? The initial value. So the charge content after will be equal to charge content before. It's a conserved quantity. Value will be C1 V1 plus C2 V2. Now our aim is to get that particular potential at which the flow will stop. We call it as the common potential. The common potential or potential after the connection. See, potential is nothing but we know that it is charge divided by capacity. So the value will be C1 V1 plus C2 V2 divided by C1 plus C2. We got the expression for the common potential, we got the expression for the charge, we got the expression for the charge, capacity after connection. So after connection, what will be the potential energy? That is another question. Potential energy of the system. Potential energy after the connection. U after, we call it as U after or maybe like U final. That is simply half C V square. Substitute for C and V, we will get half C1 plus C2 times, what is V? V is V common. C1 V1 plus C2 V2 divided by C1 plus C2 the whole square. We got the expression half 1 C1 plus C2 and the square term will get cancelled. This will be C1 V1 plus C2 V2 the whole square divided by C1 plus C2. U final. We got the expressions for everything after the connection. So hereby we have concluded everything, what is before and what is after. So before sharing and after sharing. We got the expression for the total charge, we got expression for the total potential energy, individual potentials, individual charges before connection. And after connection, what is the final capacity, charge content, common potential and potential energy. And we already mentioned that when it is connected, after connection or when it is connected, what will happen? Charge will definitely flow from the higher potential to the lower potential through the connection wires. So if there is a flow through the connection wires, we call it as an electric current. That means there is an instantaneous current flowing through that one. Till which moment? Till they attain a common potential. So during that flow, what happens in the wires? Definitely there will be a rise of temperature, or we call it as a heating effect of electric current, or we say that there will be a loss of energy in the form of heat. There is a loss of energy in the form of heat. From where that energy comes from? We know that energy is conserved. No external agency is acting on here. Wherever this heat energy is produced is only from the potential energy of the system itself. So our aim is to find out what is the amount of heat produced, or we have to quantitatively measure the amount of heat produced in the process of sharing of charges. So that heat will be the difference of which one? The potential energy initial and potential energy final, because no external energy is given into the system. As per the energy conservation, its heat is definitely a loss of energy, so that must have arisen from initial to final difference. So that is what we are going to see, the heat energy produced in the system, or heat produced is equal to delta U, we can say U before minus U after, or U final, whatever you call it as. So let us substitute the expressions and try to rearrange. Let us find out. U before is half C1 V1 square plus half C2 V2 square, and finally half we have C1 V1 plus C2 V2 the whole square divided by C1 plus C2. I'm taking half C1 C2 as common, so half C1 plus C2. On the numerator, which are the factors arise? C1 multiplied to this one will give me C1 square V1 square. So C1 square V1 square. C2 multiplied will give me C1 C2 V1 square plus C1 C2 V2 square plus C2 square V2 square. Now moving on to this, that will be minus of, take a plus b whole square, that is C1 square V1 square plus C2 square V2 square plus 2 C1 C2 V1 V2. That is what which is remaining. C1 square V1 square and C2 square V2 square cancels. I can take C1 C2 as common from all the terms which is existing on the numerator. So my expression will become half C1 C2 divided by C1 plus C2. What is remaining? V1 square plus V2 square minus 2 V1 V2. That is nothing but V1 minus V2 the whole square. So this is the expression for change in potential energy, or this is the amount of heat produced in the system. We can see when the capacitors share the charges, there is a loss of energy that arises as what? The amount of heat produced in the connection wires. We have seen the concepts, we have seen the common potential, we have seen the change in potential energy. I hope all of you must have followed this process and all of you must have understood the sharing of charges in detail. Thank you all for watching the session, and keep watching and keep sharing and keep following. Thank you all. Thank you very much.